Every plant, animal, fungus, and microorganism living today can be traced back to the first forms of life that appeared on Earth billions of years ago. At that time, the planet was very different from the modern world. The surface was still changing, volcanoes were common, oceans were forming, and the atmosphere contained gases unlike those found today. From these small beginnings, life gradually spread through the oceans, adapted to changing conditions, and evolved into countless forms. The early Earth began forming within a vast cloud of gas and dust that surrounded the young sun. This cloud contained small solid particles made of rock and metal, along with gases such as hydrogen and helium. Over a long span of time, this material slowly moved and changed position under the influence of gravity. Small particles frequently came into contact with each other, sticking together and forming slightly larger clumps. These clumps continued to grow as more material joined them. The process continued over an extended period until many solid bodies of different sizes existed within the region where the planets were forming. In the inner region of the solar system where Earth would eventually exist, the temperature was high enough that only certain materials could remain solid. Metal grains and rocky particles were more stable in this region, while lighter gases were less likely to remain close to the forming planet. As time passed, these solid particles began to gather into larger structures through repeated collisions. Each collision added mass and changed the shape of the growing bodies. Some collisions were gentle and resulted in sticking, while others were more forceful and caused breakage and reformation. Despite this, the general trend involved gradual accumulation of material. Over a long period, these growing bodies became planetesimals. Planetesimals were solid objects that varied in size, some small and others large enough so to exert their own gravitational pull. As these objects moved within the same region of space, they interacted frequently. Their gravity caused them to attract additional surrounding material, increasing their size further. The region where Earth was forming contained many of these planetesimals, and their continuous movement led to repeated interactions and merging events. As the process continued, some planetesimals grew significantly larger than others. The largest of these bodies had a stronger gravitational influence and were able to gather more surrounding material. Earth formed through this gradual accumulation of material over a long period. The material that formed Earth included rocky fragments, metallic elements, and dust particles that had been present in the early solar system. These components were drawn together into a single growing mass that increased steadily in size. During this time, the energy released by continuous impacts caused heating within the growing planet. Each collision added energy to the system, and the internal temperature increased as more material accumulated. The heat generated by these impacts contributed to the melting of some of the internal materials. The early Earth experienced a phase in which large parts of its interior were in a molten state. Heavy elements such as iron and nickel began to move toward the center of the planet under the influence of gravity, while lighter materials remained closer to the surface. This movement of materials led to the formation of distinct internal layers. The central region became enriched with dense metallic elements, forming what would later be recognized as the core. Surrounding this central region, less dense rocky material formed a thick layer. This layer would later become known as the mantle. At the outermost part, a thin solid surface gradually developed as cooling occurred in certain areas. The separation of materials based on density was a direct result of the heating and movement within the early Earth. The surface of the early Earth was not stable. It was constantly affected by impacts from remaining planetesimals and smaller fragments that continued to travel through space. These impacts added additional energy to the surface and contributed to ongoing changes in shape and temperature. Some of the impacting objects were large enough to cause extensive melting in localized regions. The surface therefore remained in a dynamic state, with areas forming and reforming over time. As the internal temperature remained high, large portions of the planet were covered by molten rock. This condition is often described as a global-scale molten phase. During this stage, the movement of molten material within the planet was active. Hot material from deeper regions rose toward the surface while cooler material sank inward. This circulation contributed to the ongoing redistribution of heat within the planet. At the same time, gases were released from the interior of the planet through volcanic activity. These gases included water vapor, carbon dioxide, nitrogen, and other volatile substances. As these gases accumulated around the planet, they formed an early atmosphere. This atmosphere was not stable in the same way as later atmospheric conditions. It was dense and contained a mixture of gases released from the interior. The composition of this early atmosphere changed gradually as more material was released and as interactions occurred at the surface. Water vapor present in the atmosphere began to condense as the planet slowly cooled in certain regions. This condensation led to the formation of liquid water, which collected on the surface in low-lying areas. Over time, these accumulations of water expanded and formed early bodies of liquid water on the planet's surface. This process occurred over an extended period as cooling continued and as more water vapor was released from the interior. The surface of the young Earth also experienced constant reshaping due to volcanic activity. Molten material from beneath the surface reached the exterior through openings in the crust. When this molten material reached the surface, it spread out and cooled, forming new solid rock. This repeated process contributed to the development of a changing surface layer that was continuously renewed and altered. The energy present within the planet remained high for a long time. This energy came from the accumulation of material, internal movement, and radioactive decay of certain elements. Radioactive elements within the planet released energy as they broke down into more stable forms. This release of energy contributed to maintaining high internal temperatures, which affected the structure and behavior of the planet's interior. As the internal structure continued to develop, the separation between different layers became more defined. The dense metallic core remained at the center, while the surrounding rocky layer formed a thick shell around it. The outermost layer remained thinner and was subject to ongoing changes due to surface activity. The interaction between internal heat and surface conditions continued to shape the planet over long periods. The early atmosphere played an important role in shaping surface conditions. It contained gases that interacted with the cooling surface and with water vapor. Chemical reactions occurred between atmospheric gases and surface materials. These interactions contributed to changes in the composition of both the atmosphere and the surface environment. The atmosphere also helped retain heat around the planet, influencing temperature conditions at the surface. As time continued, the rate of external impacts began to decrease. Fewer large objects collided with the planet, although smaller impacts still occurred. The reduction in large impacts allowed surface conditions to become less disrupted. This change supported the gradual stabilization of surface regions, although volcanic activity remained active in many areas. The movement of internal materials within the planet continued to influence surface features. Hot material rising from deeper regions caused changes in the structure of the outer layer. As this material reached the surface and cooled, it added new layers of rock. These processes contributed to the gradual development of a solid outer crust, although this crust remained subject to continuous modification due to ongoing internal activity. The presence of liquid water on the surface increased over time as more water vapor condensed and accumulated. This water interacted with surface materials and contributed to chemical changes. The distribution of water across the surface was influenced by temperature variations and surface topography. Areas of lower elevation collected more water, while higher areas remained exposed to the atmosphere and volcanic activity. The young planet continued to experience significant internal movement. Material within the mantle moved in slow cycles driven by heat from the interior. This movement affected the distribution of heat and materials within the planet. The interaction between the mantle and the outer layer contributed to changes in the structure of the surface over time. The core remained extremely hot due to the energy released during formation and continued radioactive decay. The movement of metallic elements within the core contributed to the development of internal dynamics. These dynamics influenced the generation of magnetic properties within the planet. The separation of metallic elements into the central region played a key role in the internal structure. The surface conditions of the early Earth were influenced by continuous interactions between internal heat, atmospheric gases, and liquid water. These interactions occurred over long periods and resulted in ongoing changes to the environment. Volcanic emissions continued to release gases into the atmosphere while cooling processes allowed solid structures to form in certain regions. The atmosphere itself underwent gradual changes in composition as gases were added and removed through surface interactions. Some gases reacted with surface materials, while others remained in the atmosphere for extended periods. These changes affected the density and composition of the atmospheric layer surrounding the planet. The formation of solid crustal regions occurred in areas where cooling was sufficient to allow molten material to solidify. These solid regions were later affected by additional heating and melting events, which altered their structure. The balance between cooling and heating processes played an important role in shaping the outer layer of the planet. The presence of water on the surface contributed to additional chemical interactions. Water interacted with volcanic rock and dissolved certain materials, leading to changes in surface composition. These processes influenced the distribution of elements across the planet's surface. Internal heat continued to drive movement within the planet for a long period. This movement affected both the mantle and the crust, causing shifts in material distribution. The ongoing release of energy from radioactive elements contributed to maintaining high internal temperatures. The early Earth was a place filled with intense heat, strong movement, and constant physical change. It was not a calm planet with stable land, clear skies, and quiet oceans as it is often seen today. Instead, it was a world where the surface was unstable, the ground was often reshaped, and the environment was influenced by powerful forces coming from inside and outside the planet. The material that formed Earth came together from dust, rock, and gas in space. And as this material gathered and compressed under gravity, it released a large amount of energy. This energy caused the young planet to become extremely hot, with large parts of it melting into liquid rock. At this stage, Earth was not yet a stable, solid planet with continents and oceans in their present form, but rather a growing body undergoing continuous physical change. During this early period, the surface of Earth was frequently affected by strong volcanic activity. The interior of the planet was still cooling from its formation, and heat from radioactive materials inside the planet also added to this energy. This heat caused rock deep below the surface to melt into magma. Because magma is lighter than solid rock, it often rose upward through cracks in the crust. When it reached the surface, it erupted as lava, spreading across wide areas and forming new layers of rock as it cooled. These eruptions were not rare events. They happened repeatedly across different parts of the planet, making volcanic activity a constant feature of the early Earth. The surface was repeatedly covered and reshaped by flowing lava, ash, and gases released from inside the planet. The atmosphere of the early Earth was also very different from what exists today. It was filled with gases released from volcanic eruptions, including water vapor, carbon dioxide, nitrogen, methane, and other gases. There was little to no free oxygen in the air at that time. The thick atmosphere was unstable and constantly changing due to ongoing volcanic emissions. Heat from the surface and the atmosphere interacted in a way that kept the planet in a highly active state. The high level of volcanic gases also contributed to strong weather systems, although these systems were very different from modern weather patterns. Instead of stable rain cycles and predictable winds, the early Earth experienced irregular atmospheric movement driven by heat and gas release. At the same time, the surface of Earth was frequently struck by objects from space. The early solar system still contained many leftover pieces of rock and metal that had not yet formed into planets or moons. These objects traveled through space at high speed and often collided with Earth. Each impact released large amounts of energy, producing extreme heat and shock waves. When these objects hit the surface, they created deep craters and caused surrounding rock to melt or break apart. Some impacts were large enough to affect wide regions of the planet, causing local melting and reshaping of the crust. These collisions were not occasional events but happened repeatedly over long periods of time. The combination of volcanic activity and external impacts created a surface that was always changing. The crust of the early Earth was not a single, stable layer, but a thin, broken surface that shifted and moved. New crust was created by volcanic eruptions, while other parts were broken apart or melted by impacts. In some regions, the surface cooled enough to form solid rock, but even these areas were often reshaped by later events. The early crust was constantly being rebuilt and destroyed as energy moved through the planet's interior and exterior. Inside the planet, movement of heat played a major role in shaping the surface. Hot material from deeper layers rose upward, while cooler material sank downward. This movement created strong internal circulation that affected the crust above. As magma moved beneath the surface, it caused cracks and shifts in the outer layers. These movements were not slow or gentle, they were driven by strong heat differences and caused continuous deformation of the surface. The crust could bend, crack, and shift as internal forces pushed against it. This process created a planet that was always in motion, even when the surface appeared solid for short periods. Water also began to appear on early Earth as the planet cooled slightly in some regions. Water vapor released from volcanic activity condensed into liquid form when temperatures allowed. This water collected in low areas, forming early bodies of water. However, these early water formations were unstable because the surface temperature often changed due to volcanic eruptions and impacts. Large amounts of water could evaporate quickly when nearby volcanic activity released heat or when an impact event occurred. Water on the early Earth was part of a cycle that was not yet stable or consistent. The interaction between water, rock, and heat created conditions where the surface was constantly being altered. Lava flows could enter areas containing water, causing rapid changes in temperature and pressure. This could reshape both the rock and the water environment. In some cases, water could be completely vaporized by nearby volcanic activity or impacts. In other cases, it could return after cooling periods. These changes happened repeatedly over long periods of time, making the presence of water a dynamic and unstable feature of the early Earth. The crust of the early Earth was also influenced by repeated melting and solidification. When lava cooled, it formed new rock layers. These layers could later be broken apart by new eruptions or impacts. Over time, this created a layered structure of rock that recorded the repeated cycles of destruction and formation. However, because the surface was constantly changing, these layers were often disrupted or buried by newer material. The result was a planet's surface that was uneven and constantly reshaped. Large impacts from space also had effects beyond the immediate crash site. When an object struck the surface, it released energy that traveled through the ground as shock waves. These waves could fracture rock far from the impact location. The heat from impacts could melt rock over wide areas, creating pools of molten material. Dust and debris from impacts could be thrown into the atmosphere, affecting sunlight and temperature at a global level for short periods of time. These effects added another layer of instability to the early environment. Volcanic gases released during eruptions also interacted with the atmosphere in complex ways. Water vapor could rise and later condense into rain when conditions allowed. Carbon dioxide and methane contributed to changes in temperature by trapping heat in the atmosphere. However, because volcanic activity was frequent, the composition of the atmosphere was constantly changing. This meant that surface conditions were not stable for long periods of time. The balance between heating and cooling was always shifting due to ongoing geological activity. The interior of the planet continued to release energy for a long time after its initial formation. This energy kept the surface active and unstable. Even as some regions cooled and formed solid rock, new heat from below would often break through and restart volcanic activity in those areas. The crust was thin enough that internal pressure could easily affect the surface. This made the early Earth a place where stability was temporary and local, rather than global. In many regions, repeated volcanic eruptions built large layers of rock over time. Each eruption added new material to the surface, slowly increasing the thickness of the crust in those areas. However, these same regions could later be disrupted by impacts or new eruptions. This created a cycle where the surface was built up and then broken down again. The result was a constantly shifting landscape where long-term stability was rare. The early Earth also experienced strong heating from gravitational energy. As the planet formed, collisions between smaller bodies released heat that became trapped inside the growing planet. This heat contributed to widespread melting of rock. In many areas, the surface may have been covered by large regions of molten material. These molten regions would slowly cool in some places while remaining active in others. The cooling process was uneven, leading to different surface conditions in different regions at the same time. As the planet continued to develop, the frequency of large impacts began to decrease over time. But during the early stages, these impacts were still common enough to significantly influence surface conditions. Each impact event added new energy to the system and contributed to reshaping the crust. Some impacts were powerful enough to create large basins filled with molten rock. These basins later cooled into solid formations, but they often remained sites of further geological activity due to their weakened structure. Volcanic activity and impacts also played a role in distributing elements across the surface. When rock melted and reformed, different materials could mix together. Impacts could also break apart existing rock layers and scatter material over wide areas. This mixing process contributed to a constantly changing composition of the surface. The distribution of elements was not uniform but varied, depending on local events and conditions. The early atmosphere was also affected by repeated heating and cooling cycles. When volcanic eruptions released large amounts of gas, the atmosphere became thicker and warmer. When activity slowed in certain regions, gases could condense or react with surface materials. Impacts could also temporarily change atmospheric conditions by adding dust and debris. These changes were often short-lived but frequent enough to prevent long-term stability. The surface temperature of the early Earth was highly variable. In areas near volcanic eruptions or impact sites, temperatures could rise extremely high, causing rock to melt or vaporize. In other regions, temperatures could be lower, allowing rock to solidify. This variation created a patchwork of different surface conditions across the planet. However, because of ongoing geological activity, these conditions were not permanent and often changed again. The internal structure of the planet was still organizing during this time. Heavier materials such as iron and nickel moved toward the center, while lighter materials moved toward the surface. This process contributed to the formation of the core and the early mantle structure. As this separation continued, it also released heat that contributed to surface activity. The movement of materials inside the planet helped maintain the active geological state of the early Earth. As time continued, the surface of Earth remained under constant pressure from both inside and outside forces. Internal heat drove volcanic activity and crustal movement, while external impacts added energy and disruption. The combination of these forces created a planet that was always changing in shape, temperature, and composition. The surface could not remain still for long periods because of the continuous energy flow through the system. Some regions of the surface experienced repeated cycles of destruction and rebuilding. A volcanic eruption might create a new layer of rock, followed by an impact that breaks it apart, followed by another eruption that covers it again. These cycles could repeat many times in the same area, making the geological record complex and constantly overwritten. The surface of the early Earth was therefore not a single continuous layer, but a collection of overlapping events. The interaction between molten rock and solid rock also shaped the surface in important ways. When lava flowed over solid ground, it could fill valleys, cover hills, and create new flat surfaces. As it cooled, it formed solid layers that could later be affected by new geological events. This process contributed to the uneven structure of the early crust. In many regions, layers of different ages were stacked or mixed together due to repeated volcanic activity. As impacts continued to strike the surface, some regions became heavily fractured. Cracks formed in the crust could allow magma to rise more easily, increasing volcanic activity in those areas. This created a connection between external impacts and internal processes, where one type of event could influence another. The surface was therefore shaped by a combination of both external and internal forces working together in continuous interaction. Over long periods, the energy within the planet slowly began to decrease, but during the early stages, it remained strong enough to keep the surface highly active. Heat from formation, radioactive decay, and internal movement all contributed to this energy. The result was a planet where rock was often in a molten or semi-molten state, and where solid ground existed only in temporary and changing forms. The birth of Earth's oceans began during a very early stage in the planet's long development, when the surface was still changing and the conditions were very extreme compared to what exists today. At the start, Earth was a young planet with a very hot surface, constant volcanic activity, frequent impacts from space objects, and a thick atmosphere that was very different from the air people breathe now. During this early time, water did not exist in large stable bodies like seas or oceans. Instead, water was present in different forms and came from different sources over a long period of time before it slowly gathered and settled on the surface to form the first large bodies of liquid water. Water on Earth came from both inside the planet and from space. Inside the planet, water was trapped in minerals and rocks that made up the early Earth. These materials contained hydrogen and oxygen in chemical forms. As the planet heated up due to gravitational compression, radioactive decay, and frequent volcanic activity, these materials released gases. Among the gases released was water vapor. This water vapor rose from the interior of the planet through volcanic vents and cracks in the surface. The release of gases from inside the Earth was a continuous process for a very long time during the early stages of the planet's development. This internal release of water vapor played a major role in increasing the amount of water in the early atmosphere. At the same time, another important source of water came from objects in space that collided with Earth. These objects included comets and certain types of asteroids that contained ice and frozen gases. When these objects struck the early Earth, the heat from the impacts caused the ice to melt and turn into water vapor. Some of this water vapor remained in the atmosphere while some of it eventually cooled and became liquid water. These repeated impacts over long periods added more water to the growing amount already present on the planet. The combination of internal release and external delivery made it possible for Earth to slowly build up a large amount of water. During this early period, the surface of Earth was extremely hot. The temperature was high enough to keep water in the form of vapor rather than liquid. This means that even though water was present in large amounts in the atmosphere, it could not yet form oceans on the surface. The atmosphere itself was thick and filled with gases such as carbon dioxide, nitrogen, water vapor, and other volcanic gases. Because of the high temperature, water vapor remained in the air and surrounded the planet in a dense layer. Over a very long period of time, the planet began to cool. This cooling happened gradually as the rate of volcanic heating decreased in some areas and as the planet radiated heat into space. When the surface temperature dropped enough, water vapor in the atmosphere started to change into liquid water. This process happened when the air could no longer hold all the water vapor in gaseous form. As the cooling continued, tiny droplets of water began to form in the atmosphere. These droplets combined and grew larger until they became heavy enough to fall to the surface as continuous rainfall. This rainfall was not a short event. It lasted for a very long time as water vapor continued to condense and fall from the atmosphere. The surface of the Earth, which had been extremely dry in many regions, despite the presence of water vapor in the air, began to collect large amounts of liquid water. The rain filled low areas on the surface, including basins and depressions in the crust. These low areas gradually filled up as rainfall continued over long periods. At the same time, volcanic activity still played a role in adding water vapor to the atmosphere. Volcanoes released large amounts of gases, including water vapor, which continued to feed the atmospheric water cycle. Even as rain was falling, more water vapor was still entering the atmosphere from the interior of the planet. This created a balance between water being added to the atmosphere and water being removed through rainfall. Over time, the removal through rainfall became more effective as the planet continued to cool. As the surface collected more and more water, the first stable bodies of liquid water began to form. These early bodies were not like modern oceans at first. They were smaller and less stable in the beginning stages. However, as rainfall continued and more water gathered, these bodies of water expanded and merged together. Smaller pools of water joined to form larger and deeper regions of liquid water. These regions continued to grow as long as rainfall and water accumulation continued. The structure of the early Earth's surface also changed during this time. The crust was still forming and shifting in many places. New volcanic landforms appeared, and older surfaces were reshaped by heat and movement from inside the Earth. As the surface changed, water collected in the lowest parts. These low areas became the foundation for the first large seas. The movement of the crust helped guide where water would gather, as water naturally flowed into lower regions due to gravity. As more water collected, the early seas began to expand further. These seas were shallow in some areas and deeper in others, depending on the shape of the land beneath them. Over time, continued rainfall and the addition of water from volcanic sources helped increase the volume of these seas. The water became more widespread across the planet's surface. As the accumulation continued, these seas began to connect with each other, forming larger, continuous bodies of water. During this long process, the chemical nature of the water also changed. The water that formed in the early oceans contained dissolved minerals and gases from the atmosphere and from the rocks it touched. As rain fell, it picked up gases from the air, including carbon dioxide, and carried them into the oceans. When water flowed over rocks and volcanic surfaces, it dissolved minerals such as calcium, magnesium, and iron. These dissolved substances entered the early oceans and changed their chemical composition. The early oceans were also affected by the constant interaction between water and the hot crust of the Earth. In some areas, volcanic vents released heat and gases directly into the water. This created localized areas where water chemistry was strongly influenced by volcanic materials. These interactions continued for a long time as volcanic activity remained a part of the planet's natural processes. The presence of these interactions meant that the early oceans were not uniform, but had variations in temperature and chemical content depending on location. As the oceans continued to grow, they began to cover more of the planet's surface. Areas that were once exposed land or partially dry became submerged underwater. The expansion of water coverage changed the surface environment in many ways. Water began to shape the surface through erosion, moving small particles and redistributing them across different regions. Rivers began to form as water flowed from higher regions to lower ones, carrying materials with it and transporting them into the growing seas. The formation of rivers and streams was closely connected to the development of oceans. As rainfall continued, water needed pathways to move from elevated areas to lower basins. These pathways became channels through which water flowed continuously. Over time, these channels became more established, and they carried increasing amounts of water and sediment into the seas. This process contributed to the growth and expansion of ocean basins. As the planet continued to stabilize in temperature, the water cycle became more established. Water evaporated from warm surfaces and returned to the atmosphere as vapor. It then condensed and fell again as rain. This continuous cycle helped redistribute water across the surface of the planet. Even though the early atmosphere was different from today's atmosphere, this cycle played an important role in maintaining the presence of liquid water on the surface. The early oceans also continued to receive water from ongoing impacts from space objects, although the frequency of these impacts gradually decreased over time. When impacts occurred, they released energy that could vaporize water temporarily. But as the planet cooled further, this effect became less dominant. Most of the water remained in liquid form as the surface temperature became stable enough to support large bodies of water. As more time passed, the oceans became deeper and more extensive. They began to occupy large portions of the planet's surface, filling most of the low-lying regions. The distribution of water became more balanced as the planet's surface reached a more stable state. The early seas gradually became connected into larger ocean systems, forming continuous bodies of water that covered vast areas. The interaction between water and the Earth's crust also continued to shape the structure of the ocean floors. The crust beneath the oceans was still active, with movement and changes occurring over long periods. These movements created variations in depth and structure within the ocean basins. Some areas became deeper as the crust moved apart, while other areas became shallower, due to the accumulation of sediments carried by water. Sediments carried into the oceans came from different sources. They were transported by rivers, rainfall, and surface runoff. These sediments included small particles of rock, minerals, and organic material. As they settled in the oceans, they formed layers on the ocean floor. Over time, these layers accumulated and contributed to the development of the oceanic crust structure. The chemical interaction between water and the atmosphere also continued. Gases from the atmosphere dissolved into the oceans, while gases from the oceans were released back into the atmosphere. This exchange helped regulate the composition of both the oceans and the air above them. Carbon dioxide, in particular, played a major role in this exchange, as it dissolved easily in water and influenced the chemical balance of the oceans. As the oceans became more stable, they began to influence the temperature of the planet's surface. Water has a high capacity to store heat, so large bodies of water helped moderate temperature changes on the surface. This created more stable environmental conditions in regions near the oceans. The presence of water also affected weather patterns as moisture moved between the ocean and the atmosphere. The first oceans were not uniform in shape or depth. Some areas were shallow and warm, while others were deeper and cooler depending on location and geological conditions. These variations were influenced by the structure of the crust, volcanic activity, and the continuous movement of water across the surface. The earliest atmosphere of Earth formed during a period when the planet was still assembling itself from material in space and had not yet reached a stable state. At that time, Earth was surrounded by intense heat, frequent impacts, and strong internal activity. The surface was not fixed in the way it is today, and large areas were continuously changing due to melting, solidifying, and breaking apart again. In this environment, gases began to gather around the planet, but they did not form a permanent or balanced atmosphere at the beginning. During the earliest phase, the surrounding space contained gas and dust left over from the formation of the solar system. Some of this material was drawn toward Earth by gravity. However, because the young planet was extremely hot, many of the gases that came near the surface could not remain in place for long. Heat caused them to move quickly, and many escaped back into space. This meant that any early atmosphere was constantly being lost and rebuilt again through different processes. As Earth continued to form, a major source of gases came from inside the planet itself. The material that formed Earth contained trapped gases within rocks and minerals. When the planet became hotter due to collisions and internal pressure, these trapped gases were released. This process slowly built a surrounding layer of gases above the surface. The release of gases from inside the planet continued for a very long time, shaping the composition of the early atmosphere. Volcanic activity played a central role in this stage. The early Earth had far more volcanic eruptions than exist today. These eruptions were widespread and continuous in many regions. When magma rose from deep inside the Earth and reached the surface, it released large amounts of gas. These gases included water vapor, carbon dioxide, nitrogen, sulfur gases, and small amounts of other chemical compounds. Each eruption added more material to the atmosphere, gradually increasing its density in some regions. Water vapor was one of the most common gases released. Because the surface temperature of Earth was extremely high, water could not exist as liquid. Instead, it remained as gas in the atmosphere. This water vapor accumulated over time as more volcanic eruptions occurred and as more trapped water inside rocks was released. The atmosphere at this stage held large amounts of water in gaseous form, even though no oceans existed yet. Carbon dioxide was another major component of the early atmosphere. It was produced in large quantities by volcanic activity and chemical reactions occurring within Earth's interior. Once released, carbon dioxide remained in the atmosphere for long periods because there were no living organisms to remove it. On modern Earth, plants and oceans play a major role in controlling carbon dioxide levels, but in the early atmosphere, such systems were not present. As a result, carbon dioxide built up steadily. Nitrogen was also present in the early atmosphere. It is a stable gas that does not easily react with other substances. Once released, it tended to remain in the atmosphere for long periods. Over time, nitrogen became one of the most important and long-lasting components of Earth's air. Even in the earlier stages, it was present in significant amounts, although it did not take part in many chemical reactions. Along with these major gases, smaller amounts of methane, ammonia, and sulfur compounds were also present. These gases came from volcanic emissions and chemical processes inside the Earth. Methane and ammonia were especially important in shaping the chemical behavior of the atmosphere. However, they were not stable under all conditions. Energy from the sun and chemical reactions in the atmosphere gradually broke them down over time, changing their levels. Another important source of gases was the impact of space objects. During this early period, Earth was frequently struck by asteroids and comets. These impacts were powerful enough to melt surface materials and release gases trapped within them. Comets also contained frozen gases and water, which were released when they entered Earth's hot environment or collided with the surface. These impact events added extra gases to the atmosphere in irregular bursts. Despite the continuous addition of gases, the early atmosphere remained unstable. Heat from the surface and internal activity often caused gases to escape into space. The upper parts of the atmosphere were especially affected by this loss. Lighter gases, such as hydrogen and helium, were easily lost because their movement was fast enough to overcome Earth's gravity at high temperatures. As a result, these light gases did not remain in the atmosphere for long periods. One of the most important characteristics of this early atmosphere was the absence of oxygen in a free state. Oxygen did not exist in significant amounts in the air during this stage. Any oxygen that may have formed through chemical reactions quickly combined with other elements on the surface. For example, oxygen reacted with iron in rocks, forming solid compounds that removed oxygen from the atmosphere. This process prevented oxygen from building up in the air. There were no biological sources of oxygen at this time. Living organisms that produce oxygen through processes like photosynthesis had not yet developed. Without these biological processes, oxygen had no steady source of production. This meant that even if small amounts of oxygen appeared through chemical breakdown of water or other compounds, they were quickly removed by reactions with surface materials. The lack of oxygen also meant that the atmosphere had a very different chemical structure compared to later stages of Earth's development. Many modern atmospheric processes depend on oxygen, but in this early stage, those processes did not exist. Instead, the atmosphere was dominated by gases released from volcanic activity and internal Earth processes. The chemical behavior of the atmosphere was controlled by heat, radiation, and simple reactions between gases and surface materials. Sunlight played an important role in shaping the early atmosphere. The sun emitted strong ultraviolet radiation that directly affected atmospheric gases. Without an ozone layer, this radiation reached the atmosphere and surface without much filtering. It broke apart molecules such as water vapor, methane, and ammonia into simpler parts. These broken parts sometimes recombined into new molecules, while others escaped into space due to their light weight. The absence of oxygen also meant that there was no ozone layer to protect the surface from ultraviolet radiation. This allowed more energy from the sun to reach the surface and influence chemical reactions. The atmosphere and surface were therefore strongly affected by solar energy, which helped drive changes in the composition of gases over time. As Earth gradually cooled in certain regions, some changes began to occur in the behavior of atmospheric gases. Water vapor started to accumulate in thicker layers in the atmosphere, and in some cooler areas it began to condense. However, during the earliest stage, most water remained in the atmosphere as vapor. The full formation of liquid water and stable bodies of water occurred later in Earth's history. The interaction between the atmosphere and the surface was continuous. Hot rocks and molten materials absorbed and released gases repeatedly. Carbon dioxide, for example, could be absorbed into molten rock and later released again through volcanic eruptions. This exchange created a constant cycle of movement between the Earth's interior, surface, and atmosphere. Over long periods, the balance of gases in the atmosphere slowly changed as Earth continued to evolve. Volcanic activity remained a major source of atmospheric gases, while escape of light gases into space continued. The absence of oxygen remained a constant feature throughout this early stage. The chemical building blocks of life refer to the basic substances made from carbon that can take part in the formation of living systems. These substances are present in many parts of Earth and also exist beyond Earth. They are made through natural processes that involve simple gases, energy sources, minerals, water, and time. Carbon is an element that has the ability to form many different chemical structures, because it can connect with other atoms in many stable ways. This ability allows carbon to form chains, rings, and networks that can hold hydrogen, oxygen, nitrogen, sulfur, and phosphorus. These elements together create the foundation for organic molecules that are found in all known living systems. The formation of simple organic molecules begins with basic chemical substances that contain carbon atoms. On early Earth, many simple gases were present in the atmosphere and in volcanic emissions. These gases included carbon dioxide, carbon monoxide, methane, ammonia, nitrogen, hydrogen, and water vapor. These gases were present in different regions of the planet, including the atmosphere, volcanic regions, ocean surfaces, and underground environments. The movement of these gases allowed chemical interactions to take place. When energy was introduced into these environments, chemical reactions began to produce new substances that contained carbon bonded with hydrogen and other elements. Energy sources played an important role in the formation of organic molecules. Heat from volcanic activity provided energy that allowed gases to react. Lightning provided electrical energy that broke chemical bonds in gases and allowed atoms to rearrange into new structures. Ultraviolet radiation from the sun also provided energy that influenced atmospheric chemistry. These energy sources acted continuously over long periods of time, allowing many reactions to occur repeatedly. In water environments, energy from geothermal vents beneath the ocean floor also contributed to chemical changes that supported the formation of organic molecules. Carbon dioxide in the atmosphere could interact with hydrogen and other elements under energy conditions to form simple carbon-based compounds. Carbon monoxide also took part in chemical reactions that led to the formation of molecules containing carbon and oxygen bonds. Methane, which contains carbon and hydrogen, formed under conditions where hydrogen was available in reactive environments. Ammonia, which contains nitrogen and hydrogen, contributed nitrogen atoms needed for the development of more complex organic substances. Water vapor contributed oxygen and hydrogen atoms that became part of many organic molecules. These simple substances combined in different ways, depending on temperature, pressure, and available energy. The surface of early Earth contained many active volcanic regions. These regions released gases from inside the planet. The released gases mixed with atmospheric gases and created regions where chemical reactions could occur. Hot environments near volcanic activity provided conditions where molecules could break apart and recombine. In these environments, carbon-containing gases could react with hydrogen-rich gases to form new compounds. The presence of minerals in volcanic rocks also influenced chemical reactions by providing surfaces where atoms could attach and interact. These mineral surfaces allowed molecules to come together in organized ways that supported the formation of more complex structures. The oceans on early Earth contained large amounts of water mixed with dissolved gases. Carbon dioxide from the atmosphere dissolved into ocean water and reacted with other dissolved substances. Hydrogen, nitrogen, and sulfur compounds also entered ocean water through volcanic emissions and an atmospheric mixing. In ocean water, chemical reactions occurred between dissolved gases and minerals from rocks. These reactions produced small organic molecules that remained in the water. The constant movement of water allowed these molecules to spread and interact with other chemical substances in different regions of the ocean. Hydrothermal vents on the ocean floor provided another environment where simple organic molecules formed. These vents released hot water that contained dissolved minerals and gases from deep inside the Earth. The hot water mixed with cold ocean water and created regions where chemical reactions could occur. Carbon dioxide and hydrogen in these environments reacted under heat and pressure conditions to produce simple carbon-based compounds. Iron and sulfur minerals present near hydrothermal vents also participated in chemical processes that supported the formation of organic molecules. The surfaces of vent structures provided areas where chemical substances could accumulate and interact over time. Methane played a role in early organic chemistry because it contains carbon and hydrogen. Methane could react with other gases under energy conditions to form more complex carbon compounds. Ammonia contributed nitrogen atoms that became part of organic molecules. When ammonia reacted with carbon-containing compounds, nitrogen bonds formed that became important for the development of biological molecules. Water vapor provided hydrogen and oxygen atoms that became part of many chemical structures. These elements combined in different ways to form simple organic molecules that contained carbon skeletons with attached functional groups. Formaldehyde is one of the simple organic molecules that can form from carbon monoxide and hydrogen under energy conditions. Once formaldehyde is present, it can participate in additional chemical reactions that produce other organic compounds. Hydrogen cyanide can form from carbon, nitrogen and hydrogen under certain atmospheric conditions. Hydrogen cyanide is important in chemical pathways that lead to the formation of amino acids and nucleic acid components. These molecules can form through reactions in water environments where energy sources are available. Amino acids are organic molecules that contain carbon, hydrogen, oxygen and nitrogen. They form when simpler molecules react under conditions that allow the creation of carbon-nitrogen bonds and carbon-oxygen bonds. Amino acids are important because they are the building blocks of proteins. On early Earth, amino acids could form in atmospheric conditions, in ocean water and near hydrothermal systems. The presence of carbon-containing gases, nitrogen-containing gases, and hydrogen-rich environments allowed amino acid formation to occur through multiple chemical pathways. Carbon-based compounds also form through reactions involving minerals. Certain minerals contain metal ions that can help guide chemical reactions. Iron, nickel, magnesium, and other metals found in rocks can influence how carbon atoms bond with other elements. Mineral surfaces can hold molecules in place, allowing them to interact in stable conditions. These interactions allow small organic molecules to form and accumulate. Clay minerals, in particular, provide surfaces with many small spaces where molecules can gather and undergo chemical reactions. The atmosphere of early Earth played a central role in supplying carbon-based compounds. Carbon dioxide and nitrogen were present in large amounts. Methane and ammonia were also present in varying amounts depending on local conditions. Ultraviolet radiation from the sun influenced atmospheric gases by breaking chemical bonds and allowing new molecules to form. Lightning storms provided electrical energy that triggered reactions among atmospheric gases. These reactions produced small organic molecules that could dissolve in rainwater and be carried into oceans and lakes. Rainwater acted as a transport system for simple organic molecules formed in the atmosphere. When atmospheric reactions produced organic compounds, these compounds became part of water droplets. Rainfall carried these molecules into surface water bodies. Once in water, these molecules could interact with other substances and continue chemical reactions. This process allowed organic compounds to accumulate in different environments across the planet. Carbon monoxide and carbon dioxide are important sources of carbon in organic chemistry. Carbon dioxide can dissolve in water and participate in reactions that produce carbonates and organic intermediates. Carbon monoxide can react with hydrogen to form simple hydrocarbons. These reactions occur under energy conditions such as heat or electrical discharge. Over time, these processes produce a variety of carbon-containing molecules that serve as starting points for more complex chemistry. The presence of hydrogen in early Earth environments supported the formation of reduced carbon compounds. Hydrogen atoms can bond with carbon atoms to form hydrocarbons such as methane and ethane. These hydrocarbons can undergo further reactions that introduce oxygen, nitrogen or sulfur into their structures. These modifications create functional groups that increase the diversity of organic molecules. Functional groups determine how molecules behave in chemical reactions and how they interact with water and minerals. Nitrogen is an important element in the formation of organic molecules. Nitrogen can form strong bonds with carbon, allowing the creation of amines, nitriles and other nitrogen-containing compounds. Ammonia is one of the main sources of nitrogen in early chemical environments. When ammonia reacts with carbon-based compounds, it introduces nitrogen into organic structures. These nitrogen-containing molecules are important for the development of amino acids and nucleic acid components. Sulfur is another element that contributes to organic chemistry. Sulfur can bond with carbon and hydrogen to form molecules that contain sulfur functional groups. These molecules can participate in chemical reactions that support the formation of more complex organic structures. Sulfur is often present in volcanic gases and hydrothermal vent systems. In these environments, sulfur compounds interact with carbon-based molecules and influence chemical pathways. Phosphorus is present in minerals and rocks and can enter chemical systems through erosion and water movement. Phosphorus is important in biological molecules such as nucleotides. In early chemical environments, phosphorus-containing compounds could form when minerals reacted with water and other dissolved substances. These compounds could then become part of organic molecules through chemical reactions in water environments. Simple organic molecules can accumulate in certain environments where conditions support their stability. In water bodies, these molecules can dissolve and interact with each other. In dry environments, they can remain on mineral surfaces. In icy regions, they can become trapped in frozen water structures. Each environment allows different chemical processes to occur, leading to a wide range of organic molecules. Carbon-based compounds also form in space and can arrive on Earth through meteorites. Meteorites can contain organic molecules that formed in space environments where dust, ice, and radiation interact. These molecules include simple hydrocarbons, amino acids, and other carbon-containing compounds. When meteorites enter Earth's surface, they release these compounds into the environment. These compounds then become part of Earth's chemical systems and participate in further reactions. Interstellar dust contains carbon-based molecules formed in cold space regions. In these regions, atoms and simple molecules attach to dust particles and undergo reactions over long periods of time. These processes produce organic compounds that can later be delivered to planetary surfaces. When such materials reach Earth, they contribute additional sources of carbon-based chemistry. Volcanic emissions also supply carbon-based compounds directly from the interior of the planet. Carbon dioxide and carbon monoxide, released from magma, contribute carbon atoms to surface chemistry. Methane and other hydrocarbons can also be released in smaller amounts. These gases mix with atmospheric gases and participate in chemical reactions that produce organic molecules. The interaction between water, gases, minerals, and energy sources creates many pathways for the formation of simple organic molecules. Carbon atoms can combine with hydrogen, oxygen, nitrogen, sulfur, and phosphorus in many ways. These combinations produce a large variety of molecules that contain carbon frameworks with different functional groups. These molecules can remain stable in different environments and continue to participate in chemical reactions that lead to further complexity in organic chemistry. The presence of dissolved gases in water allows continuous chemical exchange between the atmosphere and oceans. Carbon dioxide from the atmosphere enters water and reacts with dissolved minerals. Nitrogen compounds dissolve and participate in chemical reactions that produce nitrogen-containing organics. Hydrogen from various sources also participates in chemical bonding processes. These interactions allow a constant supply of carbon-based compounds in aquatic environments. Mineral surfaces provide physical support for chemical reactions. Clay minerals, iron sulfides, and other rock-forming materials create surfaces where molecules can attach. When molecules are attached to surfaces, they are positioned in ways that allow bonds to form between them. This process leads to the creation of larger organic molecules from smaller ones. The presence of many mineral surfaces in early Earth environments increases the number of places where organic chemistry can occur. The transformation of simple gases into organic molecules involves many steps of chemical change. Carbon dioxide and carbon monoxide undergo reduction reactions to form hydrocarbons. Methane can undergo oxidation or substitution reactions to form more complex molecules. Ammonia reacts with carbon compounds to introduce nitrogen into organic structures. Water participates in hydrolysis and condensation reactions that change molecular structures. These processes occur under different environmental conditions and continue over long periods of time. The accumulation of organic molecules in different environments leads to chemical diversity. In oceans, molecules mix and interact continuously. In volcanic regions, heat drives chemical transformations. In atmospheric regions, energy from radiation and lightning creates new compounds. In mineral-rich environments, surfaces guide molecular interactions. In all these environments, carbon-based chemistry continues through repeated cycles of formation and transformation. Carbon atoms have the ability to form stable bonds with many elements, which allows them to create a wide range of organic structures. These structures include straight chains, branched chains, and ring formations. Each structure allows different chemical behaviors. Functional groups attached to carbon frameworks determine how molecules interact with other substances. Organic molecules formed through natural processes can remain stable under many environmental conditions. Stability allows these molecules to persist long enough to participate in further reactions. Over time, repeated chemical interactions produce more diverse organic compounds. These compounds remain distributed across oceans, atmosphere, rocks, and space-delivered materials, continuing to participate in chemical processes that involve carbon-based chemistry. The idea known as the primordial soup hypothesis describes an early stage of Earth when the surface environment contained oceans filled with water and many dissolved chemical substances. In this view, the early oceans contained simple carbon-based molecules that were present in large amounts due to constant natural activity on the young planet. These molecules were part of a system where continuous chemical reactions took place over long periods of time. The surface of the Earth during that early period contained no living organisms, yet it held many chemical ingredients that later became important for the emergence of life. The ancient oceans formed after water accumulated on the surface of the early Earth. Water arrived and gathered in low areas where it remained for long periods. Within this water, many gases and minerals were dissolved. These included carbon-containing gases, nitrogen-containing gases, hydrogen-containing gases, and sulfur-containing gases. These gases came from volcanic activity, impacts from space objects, and chemical processes happening within the planet. When these gases entered the oceans, they did not remain unchanged. They reacted with each other and with dissolved materials already present in the water. The chemical reactions in these ancient oceans occurred continuously. Energy sources were present in different forms. Heat from volcanic vents beneath the ocean floor was one source. Electrical energy from lightning in the atmosphere was another source. Ultraviolet radiation from the sun reached the surface of the oceans due to the lack of a protective ozone layer in the atmosphere at that time. Each of these energy sources was able to cause changes in the chemical substances present in the water. Molecules gained energy, broke apart, and reformed into new combinations. Carbon played an important role in these reactions because carbon atoms can form bonds with many other elements. Carbon atoms joined with hydrogen, oxygen, nitrogen and sulfur to form a wide variety of simple organic compounds. These compounds included small molecules such as methane, formaldehyde, ammonia-based compounds, and hydrogen cyanide. These substances dissolved in the oceans and continued reacting with each other over long periods. Each reaction changed the distribution of chemical substances in the water. The ancient oceans were not uniform in their chemical content. Some regions contained higher concentrations of certain substances due to local conditions. Areas near volcanic activity contained higher temperatures and higher concentrations of dissolved gases. Areas near the surface received more radiation from the sun. Areas near mineral-rich rocks on the ocean floor contained different chemical compositions compared to open water regions. Each region contributed to different types of chemical reactions. In the absence of living organisms, chemical reactions were controlled only by physical conditions such as temperature, pressure, and energy input. Molecules in the water moved randomly due to thermal motion. When they collided, they sometimes formed temporary bonds or broke existing bonds. Over time, repeated collisions allowed more complex molecules to form. Some of these molecules remained unstable and broke apart quickly. Others remained stable for longer periods and continued to interact with other molecules. Simple organic compounds formed through these reactions included substances containing carbon chains and carbon rings. These compounds could dissolve in water or attach to mineral surfaces. Mineral surfaces on the ocean floor provided areas where chemical substances could gather and remain in close contact. This increased the frequency of reactions between molecules. Clay minerals, iron-rich minerals, and sulfur-containing minerals all provided surfaces that influenced chemical activity in the water. Energy from lightning contributed to the formation of reactive chemical substances. Lightning produced high energy bursts that passed through the atmosphere into the ocean surface. These bursts broke chemical bonds in gases and produced reactive fragments. These fragments then dissolved in water and reacted further with other dissolved substances. Each event produced a variety of new molecules that entered the ocean system and continued reacting. Volcanic vents on the ocean floor released hot water and gases into the surrounding ocean. These vents created regions where chemical activity was intense. Hot water carried dissolved minerals and gases upward into cooler regions of the ocean. As the temperature changed, chemical reactions changed as well. Some molecules formed more easily in hot conditions, while others formed more easily in cooler conditions. This variation allowed many different types of chemical substances to exist in the same environment. Ultraviolet radiation from the sun played a major role in chemical transformation. The early atmosphere contained very little oxygen and no protective ozone layer, so ultraviolet radiation reached the ocean surface in large amounts. This radiation carried enough energy to break chemical bonds in simple molecules. When bonds broke, new reactive fragments formed. These fragments then combined with other molecules in the water, producing new chemical compounds. Continuous exposure to radiation maintained a steady production of reactive chemical species. Carbon-based molecules in the oceans included chains of carbon atoms linked with hydrogen atoms. These chains varied in length and structure. Some were straight chains, while others were branched or formed ring structures. Oxygen atoms could attach to these carbon structures, creating alcohols, acids, and other oxygen-containing compounds. Nitrogen atoms could also attach, forming amines and related compounds. Sulfur atoms created additional chemical diversity. Each type of atom contributed to the variety of molecules present. Water itself played an important role in chemical reactions. Water molecules surrounded other molecules and influenced how they interacted. Water can act as a medium where molecules move freely and collide. It also participates in chemical reactions by donating or accepting small chemical groups. In this way, water was not only a solvent, but also a participant in the chemical processes occurring in the early oceans. Hydrogen cyanide formed in the atmosphere and dissolved into the oceans. Once in water, hydrogen cyanide reacted with other simple molecules to form more complex compounds containing carbon and nitrogen. These compounds included amino acid precursors and other nitrogen-rich substances. Amino acids are simple molecules that contain both carbon and nitrogen, and are important in many biological processes. In the early oceans, amino acids formed through multiple reaction pathways involving different simple compounds. Formaldehyde was another important molecule present in the oceans. Formaldehyde could react with itself and with other molecules to form larger carbon-based compounds. These reactions produced sugars and sugar-related compounds. Sugars contain carbon, hydrogen, and oxygen in specific arrangements. These molecules can dissolve in water and participate in further reactions that produce more complex chemical structures. Ammonia was present in the early environment and played a role in forming nitrogen-containing compounds. Ammonia dissolved in water and reacted with carbon-based molecules. These reactions produced compounds containing carbon-nitrogen bonds. These bonds are important in forming many types of organic molecules. The presence of ammonia increased the diversity of nitrogen-based chemistry in the oceans. Methane was also present in the early atmosphere and dissolved into ocean water. Methane contains carbon and hydrogen atoms. Under energy inputs such as radiation or electrical discharge, methane molecules could break apart and reform into larger carbon structures. These structures could then react further with oxygen, nitrogen, and other elements present in the water. Over long periods, repeated chemical reactions increased the complexity of molecules in the oceans. Small molecules combined to form larger molecules. Larger molecules sometimes broke apart into smaller molecules again. This continuous cycle created a wide range of chemical diversity. Some molecules remained stable enough to persist for long periods, allowing them to participate in further reactions. Mineral surfaces provided important environments for chemical concentration. Clay minerals contained layered structures where molecules could become trapped. Once trapped, molecules remained close to each other and reacted more frequently. Iron-containing minerals also influence chemical reactions by providing reactive surfaces. Sulfur-containing minerals contributed to reactions involving sulfur compounds and carbon compounds. Temperature variations in the ocean influenced reaction speed. Higher temperatures increased molecular motion, leading to more frequent collisions. Lower temperatures slowed reactions but allowed stable molecules to remain intact for longer periods. These variations created different chemical environments within the same ocean system. Pressure in deeper parts of the ocean also affected chemical reactions. High pressure influenced how molecules interacted with each other and with water. Some reactions occurred more easily under high pressure conditions, especially near deep ocean vents. These regions contained strong chemical gradients where substances moved from areas of high concentration to areas of low concentration. The absence of oxygen in the early atmosphere meant that many chemical reactions occurred without oxidation processes that are common in later environments. This allowed reduced chemical compounds to remain stable in the oceans. reduced compounds contain higher amounts of hydrogen relative to oxygen. These compounds participated in many of the reactions that produced more complex organic molecules. Carbon dioxide dissolved in the oceans and participated in reactions forming organic compounds. Carbon dioxide contains carbon and oxygen and can react with hydrogen-containing molecules to form more complex structures. These reactions contributed to the increasing variety of carbon-based substances in the water. Over time, the concentration of organic molecules increased in certain areas of the oceans. These areas contained mixtures of different compounds that interacted continuously. Molecules moved through diffusion and ocean currents, spreading chemical substances across large regions. This movement ensured that reactions occurred in many different environments. Some molecules formed long chains made of repeating carbon units. These chains could fold or bend in water. Folding patterns influenced how molecules interacted with each other. Certain folded structures allowed molecules to remain stable for longer periods. Stability allowed these molecules to persist through many reaction cycles. Nitrogen-containing compounds combined with carbon chains to form more complex structures. These structures included molecules that could store chemical energy in their bonds. Energy stored in chemical bonds could later be released during reactions, contributing to further chemical activity. Phosphorus compounds were also present in small amounts. Phosphorus played a role in forming molecules that could store and transfer energy. Phosphorus-containing molecules reacted with carbon and nitrogen compounds to produce additional chemical diversity. Sulfate and sulfide compounds in the oceans contributed to redox reactions. These reactions involved transfer of electrons between molecules. Electron transfer changed the chemical state of substances, allowing new compounds to form. Iron ions dissolved in water also participated in these reactions, creating additional pathways for molecular transformation. The constant interaction of all these chemical substances created an environment where new molecules continuously appeared and disappeared. Some molecules remained in the system longer than others, allowing them to undergo repeated reactions. Over long periods, this continuous process increased molecular complexity in the ocean environment. Surface films on the ocean sometimes formed where organic molecules accumulated. These thin layers contained higher concentrations of organic compounds compared to deeper water. Within these layers, molecules were in close contact with each other, allowing reactions to occur at higher frequency. These surface layers also interacted with energy sources, such as sunlight and atmospheric gases. Gas bubbles rising from volcanic vents carried dissolved chemicals upward through the water. When bubbles reach different pressure zones, they release gases and chemicals into surrounding water. This process created localized areas of high chemical concentration where reactions occurred rapidly. Certain chemical structures formed networks of connected molecules. These networks were held together by weak chemical bonds. These bonds allowed molecules to remain connected while still moving relative to each other. Such networks increased the ability of molecules to interact in multiple directions. Repeated cycles of heating and cooling in different ocean regions influenced chemical stability. Heating increased reaction speed and breaking of bonds. Cooling allowed newly formed molecules to stabilize. These cycles contributed to continuous changes in molecular populations in the ocean. The early Earth environment provided continuous sources of energy and raw materials for chemical reactions. Volcanic activity, radiation, atmospheric gases, ocean water, and mineral surfaces all contributed to this system. Each component played a role in maintaining ongoing chemical activity. Simple molecules formed more complex molecules through repeated interactions. Carbon chains grew longer through sequential reactions. Nitrogen and oxygen atoms attached to these chains in various arrangements. Sulfur and phosphorus added additional chemical variety. Each element contributed to the diversity of compounds present in the ocean environment. In some regions, chemical concentrations reached levels where multiple reactions occurred at high frequency. Molecules in these regions underwent continuous transformation, producing a wide range of organic substances. These substances remain dissolved in water or attached to mineral surfaces, continuing their chemical interactions. Energy transfer within molecules allowed bonds to form and break repeatedly. Chemical energy moved between different molecular structures through reactions. This energy flow maintained ongoing chemical transformation throughout the ocean system. The formation of increasingly complex organic compounds occurred over long periods without interruption. Each new molecule became part of a larger system of chemical interactions. Molecules influenced each other through bonding, breaking, and rearranging processes. Organic molecules containing carbon and hydrogen formed chains that could extend through many atoms. These chains interacted with other molecules containing oxygen, nitrogen, sulfur, and phosphorus. Each interaction changed the chemical structure of the molecules involved. Dissolved gases continued entering the oceans from the atmosphere and from geological sources. These gases maintained a constant supply of new chemical material for reactions. The ocean acted as a large reservoir where these materials accumulated and interacted continuously. Chemical reactions continued through cycles of formation and breakdown of molecules. Each cycle produced new substances that participated in further reactions. The diversity of chemical compounds increased as reactions continued over long periods. The environment of early Earth provided conditions where simple compounds could persist, interact, and transform repeatedly. The oceans contained water, dissolved gases, mineral surfaces, and energy sources that supported continuous chemical activity. These conditions allowed carbon-based chemistry to develop through many stages of increasing molecular complexity. Hydrothermal vents are openings found on the deep ocean floor, where heated water moves out from inside the Earth into the surrounding seawater. These places exist in areas where the Earth's crust is thin, cracked, or being pulled apart. Water from the ocean seeps down through cracks in the seafloor and gets heated by rocks that are warmed by internal heat from the Earth. This heated water then rises again and escapes through openings on the ocean floor. These systems create continuous movement of water and chemicals between the inside of the Earth and the ocean above. The environment around hydrothermal vents is dark because sunlight does not reach deep ocean regions. The pressure from the water above is very high due to the depth. Temperatures around the vent openings can change sharply depending on distance from the vent flow. Some vent fluids emerge at very high temperatures, while surrounding seawater remains very cold. These conditions create strong physical and chemical gradients in the environment. The movement of hot water from inside the Earth brings dissolved minerals and gases into contact with ocean water, producing reactions that would not occur easily in surface conditions. Hydrothermal systems are connected to volcanic activity beneath the ocean floor. Magma located under the crust heats surrounding rock and water. Water circulates through cracks in the rock, absorbs heat, and interacts with minerals. This process allows elements such as hydrogen, sulfur, iron, carbon dioxide, methane, and other dissolved compounds to move through the system. When the heated water rises and enters the ocean, it carries these substances with it. These substances can then react with each other in the surrounding environment. Two major types of hydrothermal vent systems exist. One type is associated with high-temperature fluid release from openings often called black smoker systems. These vents release dark mineral-rich plumes due to dissolved metal sulfides that precipitate when the hot fluid mixes with cold seawater. The second type is associated with alkaline vent systems where the fluid is cooler and rich in hydrogen and other dissolved compounds. Both types form structures on the seafloor made from mineral deposits that accumulate over time as fluids continuously escape and react with seawater. The interior of hydrothermal vent structures contains many small spaces and mineral surfaces. These spaces allow chemical substances to accumulate and interact in concentrated forms. Mineral surfaces can act as sites where chemical reactions occur. Iron sulfide and other metal-containing minerals are present in many vent deposits. These minerals can interact with gases dissolved in vent fluids and seawater. Chemical reactions involving hydrogen and carbon dioxide can produce simple organic compounds under these conditions. These compounds contain carbon and hydrogen atoms arranged in simple structures that form the basis of more complex chemical systems. Water circulating through hydrothermal systems brings dissolved gases from deep within the earth. Hydrogen is produced through chemical reactions between water and rock in a process involving iron-rich minerals. This hydrogen can serve as a source of energy in chemical reactions. Carbon dioxide is present in ocean water and can also enter vent systems. When hydrogen and carbon dioxide come into contact under suitable conditions, reactions can occur that produce methane and other carbon-based molecules. These reactions are driven by energy differences between reactants and products and are influenced by temperature, pressure, and mineral surfaces. The environment at hydrothermal vents contains natural chemical energy gradients. These gradients occur because different chemicals are present at different concentrations in nearby locations. Hydrogen-rich fluids emerging from vents mix with carbon dioxide-rich seawater. This mixing allows chemical reactions that release energy. The released energy can be used by chemical systems to drive additional reactions. These processes occur continuously due to constant fluid flow through the vent system. Mineral structures formed at hydrothermal vents provide physical spaces where molecules can accumulate. These spaces include pores, channels, and cavities formed during mineral precipitation. In these confined spaces, molecules remain in close contact for extended periods. This increases the probability that chemical reactions will occur. The presence of iron and sulfur minerals allows electron transfer reactions, where electrons move between molecules during chemical changes. These electron transfers are important in the formation of more complex organic compounds. The deep ocean environment surrounding hydrothermal vents contains water rich in dissolved salts. Sodium, magnesium, calcium, potassium, chloride, sulfate, and bicarbonate ions are present in varying amounts. These ions influence the chemical behavior of molecules in the environment. The high pressure conditions at ocean depth affect the way gases dissolve in water and the way molecules move and interact. Chemical reactions under high pressure can follow different pathways compared to those at lower pressure. The origin of life in hydrothermal vent environments involves the formation of organic molecules from simpler inorganic substances. Organic molecules include compounds containing carbon atoms bonded to hydrogen, oxygen, nitrogen, sulfur, and other elements. Simple organic molecules can form under conditions where energy is available and where reactive substances are present. In hydrothermal vent systems, energy from chemical gradients provides the driving force for these reactions. Carbon dioxide can be reduced by hydrogen to form simple carbon-based compounds. A key aspect of hydrothermal vent systems is the presence of catalytic mineral surfaces. Catalysts are substances that allow chemical reactions to occur without being consumed in the process. Iron-containing minerals in vent structures can serve this role. These minerals provide surfaces where molecules can attach, interact, and undergo chemical changes. The structure of these minerals includes repeating atomic patterns that can influence reaction pathways. The interaction between molecules and mineral surfaces can lead to the formation of more complex organic structures. Within hydrothermal systems, small compartments form naturally inside mineral deposits. These compartments can trap fluids and molecules, creating localized environments where chemistry is concentrated. In these spaces, molecules can undergo repeated interactions. The confinement of molecules increases the duration of contact between reactive substances. Over time, this can lead to the accumulation of more complex molecular structures. Hydrothermal vent fluids contain dissolved hydrogen sulfide in many locations. Hydrogen sulfide can participate in chemical reactions involving metal ions. When hydrogen sulfide reacts with iron ions, iron sulfide minerals can form. These minerals contribute to the growth of vent structures. The formation of these structures continues as long as fluid flow persists. The growing structures create new spaces and surfaces for chemical reactions. Organic molecules formed in hydrothermal vent environments include simple hydrocarbons, alcohols, acids, and other small carbon-based compounds. These molecules can dissolve in vent fluids or attach to mineral surfaces. Some of these compounds can undergo further reactions, leading to the formation of larger and more complex molecules. The presence of energy gradients allows these processes to continue over extended periods of time. RNA-related chemical components can form from simpler precursors under certain conditions. RNA is a type of molecule made from nucleotides. Nucleotides consist of a sugar, a phosphate group, and a nitrogen-containing base. The formation of these components requires specific chemical reactions involving carbon, nitrogen, oxygen, and phosphorus. Hydrothermal vent environments provide sources of phosphorus through mineral dissolution. Nitrogen-containing compounds can be produced from reactions involving ammonia and other nitrogen sources present in the environment. The assembly of nucleotides can occur through stepwise chemical reactions. These reactions require energy input and the presence of reactive intermediates. Mineral surfaces can assist in organizing molecules into arrangements that support bond formation. Once nucleotides form, they can link together to form short chains. These chains can remain stable under certain environmental conditions present in vent systems. Fatty acid molecules can also form in hydrothermal vent environments. These molecules have hydrophilic and hydrophobic regions that allow them to interact with water in specific ways. When present in sufficient concentration, fatty acid molecules can spontaneously form membrane-like structures. These structures create enclosed spaces that can trap molecules inside. The formation of such compartments allows chemical reactions to occur in more controlled internal environments. The movement of fluids through hydrothermal vent systems continuously supplies fresh chemical substances. This constant flow maintains the availability of reactants needed for ongoing chemical reactions. It also removes waste products from reactions, allowing new reactions to proceed. The combination of supply and removal processes supports sustained chemical activity in the vent environment. Temperature variations within vent systems influence chemical reaction rates. Higher temperatures can increase the speed of molecular movement and reaction frequency. Lower temperatures in surrounding seawater can stabilize certain molecules after they form. The interaction between hot vent fluids and cold ocean water creates zones with different chemical conditions. These zones support a variety of chemical processes occurring simultaneously. Metal ions, such as nickel, cobalt, and iron, play important roles in hydrothermal chemistry. These metals can participate in redox reactions, where electrons are transferred between molecules. Such reactions are important in building more complex organic compounds from simpler substances. Metal sulfide minerals provide surfaces where these reactions can occur efficiently. The presence of these metals in vent fluids originates from interactions between water and deep earth rocks. The chemistry of hydrothermal vents also involves gas exchange processes. Gases such as methane, carbon dioxide, hydrogen and hydrogen sulfide move between fluid phases and mineral surfaces. The solubility of these gases depends on pressure, temperature, and chemical composition of the surrounding water. Gas exchange influences the availability of reactants for chemical reactions. Organic molecules formed in hydrothermal systems can undergo polymerization reactions. Polymerization involves linking small molecules into longer chains. These processes require activation energy, which can be provided by thermal conditions or chemical gradients. Mineral surfaces can assist in organizing molecules into positions that favor bond formation. Over time, this can lead to the accumulation of longer molecular structures. The formation of compartment-like structures inside vent systems allows for separation of chemical environments. These compartments can maintain different concentrations of ions and molecules compared to surrounding seawater. The boundaries of these compartments can form from mineral walls or lipid-based structures. Within these enclosed spaces, chemical reactions can proceed under controlled conditions influenced by the local environment. Hydrothermal vent systems operate continuously due to persistent geological activity. Heat from the Earth's interior drives the circulation of water and the movement of chemicals. This continuous operation allows chemical processes to proceed over long periods of time. The repeated cycling of water through rock and ocean creates ongoing opportunities for chemical transformations. Phosphate minerals present in hydrothermal environments provide sources of phosphorus for chemical reactions. Phosphorus is important in the formation of nucleotide structures and energy transfer molecules. Dissolution of phosphate-bearing minerals releases phosphorus into vent fluids, where it can participate in further reactions. The availability of phosphorus influences the formation of complex organic compounds. Chemical energy in hydrothermal vent systems is stored in molecular bonds and gradients. When reactions occur that reduce energy differences between molecules, energy is released. This energy can drive additional chemical processes. The continuous flow of energy through the system supports ongoing chemical activity. The movement of electrons between molecules is central to these processes. Small organic molecules formed in vent environments can interact with each other to produce more complex structures. Amino acids can form under certain conditions and can link together in chains under specific chemical environments. These chains can remain stable in compartments or on mineral surfaces. The persistence of these molecules allows further chemical development over time. The structure of hydrothermal vent deposits changes as new minerals accumulate. Layers of mineral formation build upon earlier deposits. These structures create evolving environments where chemical reactions continue to take place. Fluid flow through these structures creates pathways for chemical exchange. The internal geometry of vent systems influences the movement of molecules and fluids. Deep-sea hydrothermal systems provide continuous chemical activity driven by Earth's internal heat. Water, minerals, gases, and organic compounds interact in a dynamic environment where chemical transformations occur at all times. The combination of energy sources, chemical availability, mineral surfaces, and confined spaces supports ongoing molecular processes that involve the formation and transformation of carbon-based compounds. The idea of the first self-replicating molecules is about how the earliest forms of chemistry on Earth may have reached a stage where certain molecules gain the ability to make copies of themselves. This is considered an important step in the long process that led to living systems. Before there were cells, before there were simple organisms, before there was anything that could be called life in a clear sense, there were only chemical substances interacting in water, on minerals, and in different energy environments on the early Earth. Over long periods of time, some of these chemical substances became more complex through natural processes. Among these complex substances, a few may have developed a special ability, which is the ability to influence the formation of similar copies of themselves. In the earliest stage of Earth's history, the planet had strong volcanic activity, constant impacts from space rocks, intense heat in some regions, and cooling areas where liquid water could exist. In such conditions, simple chemical compounds could form and break apart repeatedly. These compounds included small molecules made from elements such as carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. These elements were widely present on the early Earth and were involved in many chemical reactions. Water played a major role because it allowed molecules to move, collide, and interact more easily than in dry environments. In this setting, molecules were not stable in a single fixed form. They were constantly changing. Bonds between atoms were forming and breaking. Energy from lightning, ultraviolet radiation from the sun, volcanic heat, and chemical reactions in hydrothermal areas provided the driving force for these changes. In such an environment, some molecules formed chains. These chains were made of repeating units connected in specific ways. Over time, different types of molecular chains appeared, each with different structures and chemical behaviors. Among these chains, certain molecules had the ability to influence how other, similar molecules formed. This influence did not require intention or awareness. It was a result of chemical shape, bonding properties, and interaction patterns. When a molecule had a structure that allowed it to attract specific, smaller molecules and arrange them in a particular order, it could guide the formation of a copy-like structure. This process is not perfect in the beginning, but repeated chemical cycles could gradually improve the accuracy of such copying processes. The concept of self-replication in molecules refers to a situation where a molecular structure helps produce another structure that is similar in form. This can happen when the original molecule serves as a template. A template is a pattern that influences how other molecules align and bond. In early Earth conditions, molecules floating in water could occasionally come into contact with a template molecule. If the chemical attractions were suitable, smaller units in the environment could attach in a sequence determined by the template. When these attached units formed stable bonds, they could separate as a new chain, which resembles the original template. This process may have occurred in many small steps. At first, the copying process would have been extremely inaccurate. Many copies would have been incomplete or incorrectly formed. Some would break apart quickly, others might not form at all. However, because there were many chemical reactions happening continuously over large regions of the early Earth, even rare successful copying events could accumulate over time. When a molecule produced even a small number of similar structures that could also assist in similar processes, the number of such molecules could slowly increase in certain environments. One of the most important molecules in discussions of early self-replication is ribonucleic acid, commonly called RNA. RNA is a long-chain molecule made of smaller units called nucleotides. Each nucleotide contains a sugar molecule, a phosphate group, and a nitrogen-containing base. The sequence of these nucleotides along the RNA chain determines its chemical properties and its ability to interact with other molecules. RNA is capable of storing information in its sequence, and it can also perform certain chemical reactions under suitable conditions. In modern biological systems, RNA plays several roles. It helps in the transfer of genetic information from DNA to proteins. It also plays a role in regulating gene activity. In some cases, RNA molecules can act as catalysts, meaning they can speed up chemical reactions without being consumed in the process. These catalytic RNA molecules are known as ribozymes. The existence of ribozymes is important because it shows that RNA can both carry information and assist in chemical processes. In early Earth conditions before the existence of complex cells, RNA may have played a central role in molecular evolution. The idea is that RNA molecules could have formed from simpler chemical components that were available in the environment. These components include nitrogenous bases, sugars, and phosphate-containing compounds. Under certain conditions, these components can combine to form nucleotides, and nucleotides can link together to form RNA chains. Once RNA chains existed, some of them may have had sequences that allowed them to interact with other nucleotides in a way that supported copying. A single RNA molecule could attract individual nucleotides from the surrounding environment. These nucleotides could align along the RNA chain based on chemical pairing rules. In this way, the original RNA molecule could serve as a guide for assembling a complementary chain. After the complementary chain is formed, it could separate from the original, and under certain conditions, it could then act as a template itself. This type of process is considered one of the simplest forms of molecular replication. It does not require complex enzymes or cellular structures. It depends only on chemical attraction and structural compatibility between molecules. However, even in this simple form, the process would not be perfect. Errors would occur frequently. Some nucleotides might attach incorrectly. Some chains might be incomplete. Some molecules might break apart due to environmental conditions, such as heat or chemical instability. Despite these challenges, repeated cycles of formation, separation, and copying could lead to an increase in the number of RNA molecules that are better at guiding replication. This does not require planning or direction. It occurs because molecules that are more stable or more effective at guiding copying are more likely to persist for longer periods. Over time, this can lead to a gradual increase in molecular systems that support more reliable replication. The early Earth had many environments where such processes could take place. Shallow pools of water that underwent cycles of drying and refilling could concentrate chemical compounds. Mineral surfaces such as clay could provide structured areas where molecules could attach and align. Hydrothermal vents on the ocean floor could provide continuous energy and chemical gradients. In each of these environments, RNA-like molecules could undergo repeated chemical changes. In some cases, mineral surfaces could help organize nucleotides in ways that make bonding more likely. When nucleotides are held close together in a fixed arrangement, they have a higher chance of forming bonds in the correct order. This increases the likelihood that longer RNA chains could form. Once longer chains exist, they have more structural possibilities. Some of these structures can fold into shapes that allow chemical activity, including the ability to assist in further reactions. RNA molecules can fold into complex three-dimensional shapes due to interactions between their bases. These shapes depend on the sequence of nucleotides along the chain. When folding occurs, certain parts of the molecule can become active sites where chemical reactions take place. This folding ability means that RNA is not only a passive carrier of information, but also an active participant in chemical processes. In early molecular systems, this dual ability would have been important for sustaining cycles of replication. The idea of RNA as a central molecule in early life processes is supported by the fact that modern biological systems still rely heavily on RNA. In all known living organisms, RNA is present and essential for protein synthesis. The genetic code stored in DNA is first transcribed into RNA before being translated into proteins. This suggests that RNA may have existed before DNA in early evolutionary history. DNA is chemically more stable than RNA, but RNA is more versatile in terms of chemical function. In the early stages of molecular evolution, RNA molecules that could assist in their own replication would have had an advantage in terms of persistence. If a molecule can help produce more copies of itself, then it becomes more common in the environment where it exists. Over time, this leads to a higher concentration of such molecules in specific locations. These locations become chemically active regions where molecular interactions are frequent and continuous. The process of self-replication at the molecular level does not require perfect accuracy. Even systems with many errors can continue to operate if enough correct copies are produced. The key factor is that the number of successful replication events is greater than the number of breakdown events. When this balance is achieved, molecular populations can increase and diversify. RNA molecules also have the ability to undergo changes in sequence during replication. These changes can result from incorrect pairing of nucleotides or from environmental influences. Such variations produce different RNA sequences, each with slightly different chemical properties. Some of these variations may improve the ability of the molecule to replicate or to remain stable in certain conditions. Others may reduce these abilities. Over time, molecular populations become diverse, with different types of RNA structures present in the same environment. In the absence of cells, these processes would have occurred in open chemical systems. There were no membranes or boundaries like those found in modern cells. However, simple compartments may have formed naturally. For example, lipid-like molecules can form small spherical structures in water. These structures can trap RNA molecules inside them. When this happens, the RNA molecules inside a compartment can interact more frequently with each other, increasing the chances of replication events. Such compartments could also divide under physical forces such as water movement or temperature changes. When a compartment divides, the molecules inside it are distributed into smaller units. If RNA molecules inside these compartments are capable of replication, then each new compartment may contain copies of those molecules. This creates a simple system of distribution and multiplication. The combination of RNA replication, molecular variation, and compartment formation creates a situation where chemical systems become increasingly organized over time. Each step in this process depends on basic chemical interactions rather than complex biological machinery. The interactions are governed by the properties of atoms and molecules, including bonding strength, shape compatibility, and energy availability. The early Earth provided continuous sources of energy that could support these processes. Ultraviolet radiation from the sun could break chemical bonds and create reactive molecules. Lightning could provide sudden bursts of energy that drive chemical reactions. Geothermal heat from volcanic activity could maintain warm environments, where reactions proceed steadily. Chemical gradients in ocean environments could provide constant energy differences that drive molecular movement. In such environments, RNA molecules that could maintain their structure and assist in replication would tend to persist longer. Molecules that were unstable or unable to participate in replication would break down or become diluted in the environment. Over time, this leads to a natural selection-like process at the molecular level, where certain structures become more common due to their chemical behavior. The idea of RNA-based self-replication is part of a broader concept of how chemical systems transition toward more organized forms. It focuses on how simple molecules, through repeated interactions and environmental influences, can develop properties that resemble basic information storage and copying systems. RNA stands out because of its ability to store sequence information, form catalytic structures, and participate directly in replication-like processes. The emergence of the first cells on the early Earth was a long process that took place over an extremely long period of time under changing natural conditions. It involved the gradual organization of simple chemical substances into more complex arrangements that could hold themselves together, maintain internal order, and carry out basic chemical activities needed for continued existence. Before the appearance of cells, there were only non-living chemical systems made from basic elements such as carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. These elements were present in water, rocks, air, and dissolved gases. Over time, they interacted in different environments, such as shallow waters, volcanic regions, and deep ocean settings where energy sources were available. These interactions slowly produced more complex organic molecules, such as amino acids, simple sugars, fatty acids, and nucleotide components. These molecules were not alive on their own, but they were able to form larger structures under the right conditions. One of the most important early developments in this process was the formation of protective membranes. These membranes were made from simple fatty acid molecules that naturally arranged themselves in watery environments. Fatty acids have one end that is attracted to water and another end that repels water. So when many of them were present in the same environment, they naturally organized into thin layers and small spherical structures. These structures were able to trap water inside them and separate an internal space from the surrounding environment. This separation was very important because it allowed chemical reactions inside the structure to become different from those outside. Inside these simple membranes, molecules could remain together for longer periods without being dispersed by the surrounding water. This allowed reactions to continue in a more stable way, increasing the chance that more organized chemical systems could form. These early membrane structures were not yet living cells, but they created a basic boundary that is necessary for lifelike behavior. The ability to separate internal chemical conditions from external conditions made it possible for early systems to maintain a more controlled environment. This control allowed certain molecules to accumulate inside, while others were kept out or entered in limited amounts. Over time, these membrane-bound structures became more stable and more capable of maintaining their shape. Some of them could grow by absorbing additional fatty acid molecules from the surrounding environment. Others could divide when they became too large or unstable, forming smaller structures that continued the same basic organization. These processes were not directed by any plan, but were the result of natural physical and chemical properties of the molecules involved. At the same time as membranes were forming, other important chemical developments were taking place inside the early Earth environment. Simple organic molecules were combining to form longer chains and more complex structures. Amino acids began to link together in small sequences, forming short peptides. Nucleotide-like molecules began to interact and form strands of genetic-like material under certain conditions. These processes were influenced by energy sources, such as ultraviolet radiation from the young sun, heat from volcanic activity, electrical discharges from storms, and chemical energy from reactions occurring in rocks and minerals. Each of these energy sources provided the force needed to drive chemical changes that would not normally happen under low energy conditions. As these chemical processes continued, some of the membrane-bound structures began to contain more organized internal chemistry. Certain molecules inside these structures were able to influence how other molecules behaved. For example, some short chains of amino acids could make it easier for certain reactions to occur by bringing molecules closer together or by stabilizing temporary arrangements. In this way, simple chemical catalysts began to appear. These catalysts were not complex proteins like those found in modern living cells, but they were early forms of molecules that could speed up chemical reactions. The presence of such catalytic molecules inside membrane structures increased the likelihood that internal chemistry would become more organized and more efficient over time. Inside these early structures, the concentration of molecules played a key role in chemical development. When molecules were enclosed within a boundary, they were less likely to drift away, which meant that reactions could happen more frequently. This increased concentration made it possible for more complex chains of reactions to develop. Some of these reactions produced molecules that helped stabilize the membrane itself, making the structure more durable. Others produced molecules that assisted in the copying of simple genetic-like strands, allowing information to be preserved in a basic form. The ability to preserve molecular information was an important step in the development of living systems, because it allowed certain chemical patterns to persist over time instead of disappearing after a single reaction. The primitive living structures that formed during this period were not uniform. Many different types of membrane-bound chemical systems likely existed, each with different internal compositions and behaviors. Some were short-lived and broke apart quickly when environmental conditions changed. Others were more stable and could persist for longer periods. Some were able to grow by absorbing surrounding molecules, while others remained small and relatively inactive. The differences among these structures were not due to any guiding force, but were the result of variations in available molecules, energy sources, and environmental conditions at different locations on the early Earth. Water played a central role in all of these processes. It acted as a medium where molecules could move freely and interact with one another. It also helped transport dissolved substances between different environments. In some areas, water collected in pools or shallow regions where evaporation and concentration of chemicals could occur. In other areas, water circulated through hot rocks beneath the surface, carrying dissolved minerals and organic compounds. These different environments created a wide range of conditions where chemical reactions could take place. In each setting, the presence of water allowed molecules to come together and separate repeatedly, increasing the number of possible interactions over time. The formation of primitive living structures also depended on the availability of certain key elements. Carbon was especially important because it can form stable chains and rings that serve as the backbone of organic molecules. Hydrogen and oxygen were necessary for forming water and many organic compounds. Nitrogen was essential for the formation of amino acids and nucleotide bases. Phosphorus played a role in energy transfer and in the formation of molecular backbones for genetic-like materials. Sulfur was involved in some early catalytic reactions and helped stabilize certain molecular structures. These elements were widely available on the early Earth due to volcanic activity, atmospheric processes, and interactions between water and rocks. As time continued, the chemical systems inside membrane structures became more interconnected. Some reactions began to depend on the products of other reactions, forming simple networks of chemical activity. These networks allowed the system to maintain itself for longer periods, as long as external conditions remained favorable. When one reaction produced a molecule needed for another reaction, the overall system became more stable. This kind of interdependence marked an important step toward the development of more organized biological processes. The chemical networks were still simple, but they showed early signs of coordinated activity within enclosed spaces. Energy flow was also a critical factor in maintaining these early systems. Chemical reactions require energy to proceed, and the early Earth provided multiple sources of energy that could be used by primitive molecular systems. Heat from geothermal activity provided constant energy input in some regions. Ultraviolet radiation provided high-energy photons that could break and form chemical bonds. Electrical energy from atmospheric storms created short bursts of intense activity. Chemical gradients between different environments also provided energy that could be harnessed by molecular systems. These energy sources allowed reactions to continue over time and contributed to the increasing complexity of chemical structures inside membrane boundaries. The stability of early membranes improved as more complex molecules became incorporated into them. While simple fatty acids could form basic boundaries, the addition of other lipid-like molecules helped strengthen these structures. Some membranes became more resistant to environmental changes, such as temperature fluctuations or variations in water chemistry. This increased stability allowed enclosed chemical systems to persist for longer periods and undergo more cycles of internal reactions. During these cycles, molecules were repeatedly formed, broken apart, and reformed in different arrangements, leading to a gradual increase in chemical complexity. Some primitive structures may have developed the ability to maintain internal chemical gradients, where certain substances were more concentrated inside the structure than outside. This allowed the system to sustain reactions that would otherwise not occur in a uniform environment. Maintaining these gradients required energy and selective movement of molecules across the membrane boundary. Even simple forms of selective permeability could have played a role in controlling which substances entered or left the structure. This control was not precise, but it allowed early systems to maintain internal differences from the external environment for limited periods. The development of early genetic-like molecules within these structures added another layer of complexity. Short strands of nucleic acid-like material could carry simple patterns of chemical information. These patterns could influence the production of other molecules, especially if catalytic compounds were present. Some strands may have been able to copy themselves under certain conditions, although these copying processes were likely very inaccurate at first. Even with low accuracy, partial copying allowed certain molecular patterns to persist longer than others, increasing their presence in the environment over time. as more cycles of formation and breakdown occurred, certain combinations of molecules and membrane structures became more common. These combinations were those that could maintain stability for longer periods and support more internal reactions. The repeated formation of such systems increased their overall presence in suitable environments. In some locations, large numbers of membrane-bound structures may have existed at the same time, each undergoing different chemical processes. Some of these structures may have exchanged materials with each other, through merging or splitting, allowing chemical components to spread between different systems. The internal organization of these early systems remained simple, but it gradually became more structured. Molecules that were useful for maintaining stability or supporting reactions tended to remain inside the structures longer. Molecules that were less useful tended to be lost to the surrounding environment. This gradual selection of chemical components within membrane-bound systems led to increasing organization over time. Internal reactions became more focused on maintaining the structure and supporting continued chemical activity. Environmental changes on the early Earth also influenced the development of these systems. Changes in temperature, water availability, and chemical composition of surrounding environments affected which structures could survive and continue their internal processes. Some regions experienced cycles of drying and re-wetting, which concentrated chemicals and then dispersed them again. These cycles created repeated opportunities for molecules to assemble into new structures, and for existing structures to change their composition. Other regions, such as deep underwater environments, provided more stable conditions where chemical systems could persist for longer periods without interruption. Within this broad range of environments, the emergence of the first cells represented the point where membrane-bound chemical systems became capable of sustained internal organization and continued chemical activity over extended periods. These early cells were extremely simple compared to modern living organisms, but they contained the basic features required for continued existence, including a boundary membrane, internal chemical reactions, and molecular systems capable of storing and transferring basic information. The transition from non-living chemical systems to early cellular forms involved many small steps, each contributing to greater stability and organization of molecular processes within enclosed spaces. The Great Oxygenation Event refers to a very long period in Earth's early history, when the amount of oxygen in the air and oceans began to increase in a noticeable and lasting way. This change did not happen in a short time. It developed across many hundreds of millions of years during the early part of Earth's deep past, when the planet was still very young and its surface, oceans and atmosphere were undergoing continuous chemical change. Before this period, oxygen existed only in very small amounts and was quickly removed by reactions with materials in the oceans and rocks. The atmosphere at that time was mostly made of gases, such as carbon dioxide, nitrogen, methane, ammonia, and water vapor, with oxygen present only in traces that did not remain free for long. The rise of oxygen began through biological activity in the oceans. Very early forms of microbial life developed the ability to use sunlight to produce energy. These organisms lived in shallow marine environments where sunlight could reach them. During their energy production process, they released oxygen as a byproduct. At first, this oxygen did not accumulate in the atmosphere because it reacted with dissolved iron in the oceans and with volcanic gases. The oceans contained large amounts of dissolved iron in reduced form. When oxygen was produced, it immediately combined with this iron, forming solid mineral deposits that slowly settled on the seafloor. This process continued for a long period, preventing oxygen from building up in the air above the oceans. Over time, the continuous production of oxygen began to exceed the capacity of these natural sinks. The iron in the oceans gradually became less abundant in reactive form, because much of it had already combined with oxygen and settled as solid layers on the ocean floor. Volcanic gases that could react with oxygen also began to play a smaller role in consuming it. As a result, oxygen began to remain uncombined for longer periods and slowly started to accumulate in the oceans and then move into the atmosphere. This transition marked a major chemical change in Earth's surface environment. Oxygen is highly reactive, and its increasing presence changed the chemistry of both water and air. In the oceans, dissolved oxygen began to appear in greater amounts. This allowed new chemical reactions to occur that had not been stable before. Iron that remained dissolved in seawater began to oxidize more easily in certain regions, leading to the formation of additional mineral deposits. These changes created layered formations in ancient rock sequences, which recorded the progressive oxygenation of the oceans. As oxygen began to enter the atmosphere in larger amounts, it interacted with gases that were present at the time. Methane, which had been an important atmospheric gas, reacted with oxygen and gradually decreased in concentration. This reduction in methane changed the overall chemical balance of the atmosphere. Carbon dioxide also interacted indirectly with changing atmospheric chemistry through various geological and biological processes. The reduction of methane had a strong influence on the temperature balance of the planet, because methane had been an important gas involved in retaining heat in the atmosphere. As methane levels decreased due to oxidation, the atmospheric conditions shifted, leading to changes in global temperature patterns and climate stability. The appearance of free oxygen in the atmosphere also led to the formation of a protective layer of ozone at higher altitudes. Oxygen molecules in the upper atmosphere were affected by solar radiation, which caused them to separate and recombine into ozone molecules. This ozone layer began to develop gradually as oxygen levels increased. The presence of ozone changed the way solar radiation interacted with the surface environment. Before this development, ultraviolet radiation from the sun reached the surface of Earth in much greater intensity. With the formation of ozone, a portion of this radiation was absorbed before reaching lower atmospheric layers and the surface. The increase in oxygen also had strong effects on the chemistry of rocks and minerals on land and under shallow seas. Many minerals that were stable in low oxygen conditions began to change form when exposed to oxygen. Iron-bearing minerals were particularly affected. Iron that was previously in a reduced state became oxidized, leading to the formation of rust-like compounds that accumulated in soils and sediments. These changes influenced the color, composition, and structure of ancient rock layers. Over long periods, these processes created extensive geological records that show repeated cycles of oxygen presence and chemical reaction in different environments. In marine environments, the increasing oxygen levels changed the conditions for microbial life. Some microorganisms adapted to use oxygen in their energy processes. Oxygen allowed energy production to become more efficient in certain biological systems, and organisms that developed this capability were able to expand into new ecological areas within the oceans. At the same time, many early organisms that had developed in oxygen-free conditions were affected by the presence of oxygen because it was chemically reactive and could damage cellular structures that were not adapted to it. These changes influenced the distribution of microbial communities across different ocean regions. The rise of oxygen also influenced the cycling of elements such as carbon, sulfur, and nitrogen. In low oxygen environments, these elements often remained in reduced forms, but with increasing oxygen availability, they began to shift into oxidized forms. Carbon compounds became more involved in carbon dioxide cycles, involving both biological and geological processes. Sulfur compounds were transformed into sulfate forms in many environments, which affected sediment chemistry in marine basins. Nitrogen cycles also began to develop new pathways involving oxidation reactions that changed how nitrogen moved between the atmosphere, oceans, and sediments. The physical structure of the oceans also responded to increasing oxygen levels. Oxygen entered surface waters first and then gradually spread into deeper regions, depending on mixing processes and biological activity. In some deep ocean areas, oxygen remained limited for long periods because of restricted circulation and continuous consumption by decomposing organic material. This created differences in oxygen distribution at different ocean depths, which influenced chemical reactions and sediment formation in those regions. As oxygen continued to accumulate in the atmosphere, its presence began to affect weathering processes on land. Rocks exposed at the surface interacted with oxygen, leading to increased chemical breakdown of certain minerals. Water flowing over land surfaces carried dissolved oxygen, which contributed to these reactions. Over long periods, this influenced soil formation and the movement of elements from land into the oceans. River systems became important pathways for transporting oxidized materials, which then contributed to further chemical changes in marine environments. The increase in atmospheric oxygen also influenced volcanic gas chemistry. Volcanic eruptions released gases such as sulfur dioxide, carbon dioxide, and hydrogen sulfide. When these gases interacted with oxygen in the atmosphere, new chemical reactions occurred that changed their composition. Sulfur dioxide could be transformed into sulfate particles, which then entered atmospheric circulation and eventually returned to the surface through precipitation. These processes affected atmospheric composition and the chemical balance between volcanic emissions and atmospheric gases. During this long period of oxygen increase, the Earth's surface experienced changes in the distribution of mineral deposits. Large accumulations of iron-rich minerals formed in ancient sedimentary layers during times when oxygen production was active in the oceans but still interacting strongly with dissolved iron. These deposits became part of the geological record of oxygen activity in early Earth environments. Other minerals also formed in response to changing redox conditions, including manganese compounds and various iron oxides that appeared in different sedimentary settings. The biological production of oxygen continued as microbial life expanded in ocean environments. These organisms relied on sunlight and dissolved materials in seawater to sustain their energy processes. Their activity influenced not only oxygen levels, but also the chemical composition of surrounding waters. Organic material produced by these organisms sank into deeper ocean layers, where it was broken down through chemical and biological processes. This decomposition consumed oxygen in some regions while releasing nutrients that supported additional microbial activity in surface waters. As oxygen levels increased further, atmospheric chemistry became more stable in certain ways. Reactive gases that had previously existed in higher concentrations were reduced through oxidation processes. This led to changes in the overall composition of the atmosphere and influenced the behavior of gases involved in climate regulation. The balance between oxygen production and oxygen consumption gradually shifted toward conditions where oxygen could remain present in the atmosphere for extended periods without being completely removed by chemical reactions. The changes in atmospheric oxygen also influence the density and structure of the atmosphere. As oxygen accumulated, it became a significant component of the gas mixture surrounding the planet. This influenced how gases were distributed vertically and how they interacted with solar energy. The absorption and scattering of sunlight were affected by the presence of oxygen and its related compounds, contributing to changes in atmospheric energy flow and surface conditions. In ocean chemistry, the presence of oxygen allowed for the formation of new types of mineral precipitation in certain environments. Iron and other metals dissolved in seawater could react with oxygen to form solid particles that settled to the seafloor. These processes contributed to the layering of sediments over long periods. Chemical gradients developed between oxygen-rich and oxygen-poor regions of the oceans, and these gradients influenced the movement of chemical species and the structure of marine environments. The gradual oxygenation of Earth's atmosphere and oceans also influenced the long-term stability of surface conditions. Chemical reactions involving oxygen affected greenhouse gases, mineral cycles, and biological processes in ways that continued over extended geological time. These processes interacted continuously, shaping the evolution of the planet's surface chemistry, ocean structure, and atmospheric composition across vast spans of time, while oxygen continued to accumulate in varying amounts in different environments, influencing ongoing chemical transformations across the Earth system without reaching a final stabilized state. Life on Earth today can be traced back to a single ancient population of organisms that existed very early in the planet's history. This population is called the last universal common ancestor. It was not one single living creature, but a group of very early microscopic life forms that shared the same basic biological system. From this group, all living things that exist today eventually developed over an extremely long span of time. Every bacterium, every archaeon, every plant, every animal, and every fungus shares this deep origin. All living organisms show strong similarities at the most basic level, even when they look completely different in form and lifestyle. These similarities are found in the way cells store information, how they build proteins, and how they produce energy. The presence of these shared systems across all life forms suggests that they were inherited from a single ancient source rather than appearing separately many times. One of the clearest signs of this shared origin is the genetic system used by all known life. Every organism uses DNA as the main molecule for storing biological information. DNA is made up of 4 chemical units arranged in long sequences. These sequences act as instructions that guide the building and functioning of cells. The fact that all life uses the same 4-letter system strongly points to a shared beginning. If life had started independently in different places, it would be highly unlikely that every system would settle on the same chemical code without variation. The method used to read genetic information is also nearly identical in all organisms. Cells read DNA in groups of 3 letters at a time. Each group of 3, called a codon, represents a specific amino acid. Amino acids are the building blocks of proteins. In almost all organisms, the same codons correspond to the same amino acids. This consistency across bacteria, archaea, and eukaryotes shows that the genetic code was already established before these groups separated and then passed down through all later life forms. Proteins provide another strong line of evidence. Proteins carry out most of the functions inside cells, including structure, movement, and chemical reactions. All known organisms use the same basic set of about 20 amino acids to build proteins. This shared set of building blocks is extremely consistent across all life. It suggests that the protein building system was already present in the earliest shared biological system and was inherited by everything that followed. Inside every cell, a structure called the ribosome is responsible for building proteins. Ribosomes are found in all organisms and perform the same essential job of reading genetic instructions and assembling amino acids into proteins. Although there are small differences between species, the core structure of ribosomes is highly similar everywhere. Ribosomal RNA, a key component of ribosomes, changes very slowly over time. Because of this slow change, it acts as a long-lasting record of evolutionary history. When scientists compare ribosomal RNA across many organisms, they consistently find patterns that point back to a single, ancient origin. These comparisons are used to construct evolutionary trees that show how different life forms are related. All of these trees, even when built using different methods, lead back to one deep branching point. That point represents the last shared ancestral population from which all modern life emerged. The repeated appearance of this same branching pattern in many studies strengthens the conclusion that all life shares a single origin. Energy systems in cells also provide strong evidence of common ancestry. All living organisms require energy to survive and carry out biological processes. A universal molecule called adenosine triphosphate is used as the main energy carrier in all known life. This molecule is produced and used in very similar ways across all organisms. One of the most important structures involved in this process is ATP synthase, a molecular machine found in bacteria, archaea, and eukaryotes. It has a very similar structure and function in all these groups, suggesting that it already existed in the earliest shared biological system. The process of copying genetic material is another shared feature. All cells must replicate their DNA before they divide. This is done using enzymes known as DNA polymerases. These enzymes are present in all organisms and show deep similarities in how they function. Even though there are variations, the basic mechanism of DNA replication is conserved across all life forms. This indicates that a primitive version of this system existed very early and was inherited through all later evolution. Cell structure also supports the idea of a shared origin. Every living cell is surrounded by a membrane made of lipid molecules. This membrane acts as a barrier that separates the inside of the cell from the outside environment and allows controlled chemical activity within the cell. While the types of lipids can vary between major groups of organisms, the existence of a membrane boundary is universal. This suggests that early life already had a way to maintain a protected internal environment. Certain genes are found in almost all living organisms. These genes are responsible for essential processes, such as reading genetic information, building proteins, and maintaining cellular function. Their widespread presence across all forms of life indicates that they were already present in the ancestral population. Over time, these genes changed in different directions in different lineages, but their core roles remained the same. The complexity of the systems shared by all organisms also supports a common origin. Processes like protein synthesis involve many components working together in precise coordination. These systems are so complex and so similar across all life forms that it is difficult to explain their presence without assuming inheritance from a single early biological system. The shared structure of these systems points toward a common starting point in the history of life. Direct fossil evidence from this ancient time is extremely rare because early organisms were microscopic and lacked hard parts that fossilize easily. Because of this, most knowledge comes from studying modern organisms. Scientists compare DNA sequences, protein structures, and cellular machinery to reconstruct relationships between all living things. These comparisons consistently point back to a single ancestral population. This ancestral population already had a working genetic system, a method of protein production, and a way to generate energy. These features allowed it to reproduce and pass information forward. Over a very long time, its descendants diversified into all forms of life seen today, while still retaining many of the same basic biological systems that originated in that early stage of Earth's history.